Welcome to chemistry. If you're watching this, you probably just began a chemistry class, and I hope to make things easier for you with my videos. If you just began a chemistry class, the other thing you are probably doing is sitting there thinking, am I accidentally in history class? Because often what they'll do is they'll bombard you with the names of all these old dead guys that made discoveries about the atom and helped us understand what we understand about the atom today. So in this video, I hope to clear up what each of these guys did, because they can get confusing, and also to give you an idea of how we see the structure of the atom and how our view of the atom has changed over time. So here is the atom. It has a nucleus, and then it has a surrounding cloud of electrons. So the atom is one unit, and then it's got subatomic particles, which are particles even smaller than the atom. And we don't usually break these down in chemical reactions, but we have done it. It has happened. We have broken down an atom past the atom to the subatomic particles. But when you think of an atom, you should think of the nucleus, which has protons and neutrons, and the surrounding area, which has electrons. Most of the mass of the atom is made up of protons and neutrons. An electron is many, many, many times less massive than a proton or neutron, and you'll find when we start calculating masses, we usually just leave the electrons out because they're so freaking small. So the protons and neutrons in the nucleus also do not take up very much space. They have most of the mass, but not very much of the volume. And the electrons on the outside are going to take up a lot of space, but again, they are small. They're smaller than the protons and neutrons. So the way that my chemistry teacher told me to think of it was, if your atom is like a stadium, then the electrons are like flies buzzing around the stadium. Yes, that is an accurate analogy in terms of size. Electrons are teeny tiny, and you probably can't even begin to fathom, I know I can't, how small they actually are, even in comparison to the nucleus, which is already small itself. But the protons are positive, the neutrons are neutral, and both of those have an atomic mass of 1 mass unit, and then the electron is really tiny, and when you are asked about how massive is the electron, you could just say the mass is so small it is negligible. We don't care. So when we look at the periodic table of the elements, and the website that I recommend that I always use is ptable.com, and I'm going to have a whole video dissecting how the periodic table works and how to read it. You're going to see each element in these little boxes. So for example, I have oxygen here, and we see 2 numbers. This is called the atomic number, and it tells us how many protons are in our element. How many protons defines the element. If I change this to 9 protons or 10 protons, I'm not oxygen anymore. I'm fluorine or neon. There's also this number, which is the mass number. The mass number is going to tell us the average mass of the element. So when I say average, I mean a weighted average of different isotopes. Well, what the heck is an isotope? So you know how every atom of a given element, for example, every oxygen atom is going to have the same number of protons. In the case of oxygen, 8. Not every oxygen atom has the same number of neutrons. Because they're neutral, they don't do a lot except for just sit there and make the atom heavier. So we can have different neutrons and still have it be oxygen, meaning that it will still act the same and participate in the same chemical reactions. So for example, we can have oxygen 16, we can have oxygen 18. And people have looked at different isotopes of each element and figured out how abundant are they in the universe. So for example, with carbon, carbon-12 is many, many more times abundant than carbon-13. And those, as a reminder, are 2 different isotopes of carbon. And in these notations, when we see isotopes, you have the atomic number written at the bottom and the atomic mass written at the top. And why is it all of a sudden not a decimal? Well, it's not a decimal because this decimal is a weighted average. So for example, if I had 75% of one isotope and 25% of another, and that's how abundant they are in our known universe, then I would take the 75% mass and multiply it by 3/4. I would take the 25% abundant mass and multiply that by 1/4, add them up, and get a weighted average. And because you're multiplying by fractions, you get a decimal. And I know that sounds very confusing. I want to make a whole video on how to take a weighted average. So don't worry about that too much here. But the point is, when you have one isotope by itself, this isotope doesn't have a decimal because you can't have a decimal number of protons or neutrons. You have to have a discrete number, aka 1, 2, 3, 4. So here, because we know we have 8 protons, 18 in this one, which is the protons and the neutrons, tells us we have 8 protons and 10 neutrons. So the number of neutrons is not directly on these notations, but we can deduce it. Well, that's all very cool, but how did we discover that it's like this? How did we find out the structure of the atom? Well, this started long ago, before the scientific method. In ancient Greece, the way people did science was they just kind of put out hypotheses, and they didn't really know how to test them. So Leucippus and Democritus put out this hypothesis that matter, which is anything that has mass, can be broken down into atoms, which were building blocks, and you can't break them down anymore. So an atom would have a certain size, all atoms would have the same size, and then once you get down to an atom, you can't break it down anymore. Now, again, there was no way to test this, and there was another theory floating around at the time, and that theory was the theory from Aristotle. And Aristotle said that elements were made of earth, water, air, and fire. And if you combine them in different ways, then you get different stuff. And they also could be broken down in such a way that, like, there was no atom, there was no building block. In Aristotle's theory, you can break it down as much or as little as you want. There was no discrete mass where it's like, this is an atom, you can't break this up. So there was no way to test this. So Aristotle's theory actually prevailed for many, many years until we started analyzing chemical reactions and developing the scientific method. And at this point, we were able to figure out some laws, and these laws helped us figure out how an atom worked. So the first of these laws is called the law of conservation of mass. Law of conservation of mass says we cannot poof matter into existence or out of existence. We can't create or destroy matter. Matter is constant in the universe. So for example, if I have a chemical reaction and I react 28 grams of N2 and 32 grams of O2, how much product am I going to get? Well, it has to be 60 grams of NO, because if it's not 60 grams, if it's 59, where did the 1 gram go? It went just poof, magically out of existence. We don't poof. If we were 61 grams in the end instead of 60, we have poofed a gram into existence. So law of conservation of mass says we can't do magic in chemistry. We can't just poof things into and out of existence. And then we have these two laws, which people confuse, but I'm going to try to make them distinct for you. So the law of definite proportions has to do with the fact that if you have a compound, which is a combination of two elements, and if you have different weights of that compound, the elements in the compound will have the same ratios of mass within that compound. So for example, if we look at NO, then we would have 1 gram of nitrogen would go with 1.14 grams of oxygen. But if we have 2 grams of nitrogen in our sample of NO, we would have to have 2.28 grams of oxygen. So these guys always combine in that ratio, where if you were to do percent by mass, you would get 46.7% N, 53.3% O, and it would always be like this no matter how much or how little of the NO that you have. Now this is not going to be the same for every element, meaning that if you had CO or H2O or like NaCl or any other compound, these things would have different mass ratios compared to each other. But if you have like 5 grams of NaCl, 10 grams of NaCl, 15 grams of NaCl, the mass ratio of Na to Cl is always going to be the same. Law of definite proportions has to do with only one compound at a time. In the law of definite proportions, we don't compare two compounds. We compare different masses of the same one compound. The law of multiple proportions has to do with comparing multiple compounds. And in this one, what we like to do as an example is we like to show two compounds where they have one of one element and then we change the amount of the other element. So for example, NO versus NO2. And if we keep the mass of nitrogen constant in these samples at 1 gram, then if we go from NO to NO2, the mass of oxygen in the compound doubles. So this says that if you have two elements combining, these mass ratios are always going to work out to be like whole number type things. Like you're never going to have the mass of one thing remain constant and the mass of the other thing multiply by like 1/7. So the law of multiple proportions is kind of telling us that we have these discrete building blocks because we can't have a graph that looks like this. and has the same nitrogen here. And again, NO and NO2 are only examples, and you can do this with lots and lots of different compounds. But bottom line is the law of definite proportions has to do with one compound at a time. The law of multiple proportions compares to compounds that have the same elements in them. So with these three laws, this guy named Dalton, who actually figured out the law of multiple proportions, he was able to come up with a picture of what he thought the atom was like. And Dalton's view of the atom is very boring. It's just a circle, right? Because he didn't know about charges. He didn't know about protons and neutrons and electrons. He just thought we can break things down into atoms, and we can't break it down anymore. So he was taking from his old predecessors, Leucippus and Democritus. And he put forth these points. Elements are composed of tiny indestructible particles called atoms. This one is still correct today. We still think of this as true. It is true. Some books will say indivisible, indestructible particles in these points. And you are not meant to memorize these points word for word. You just need to know, like, if you're given multiple choice, like which of these did Dalton come up with, to know to recognize them. But if the point said indivisible, that would not be true, because we do have subatomic particles. We have protons, we have neutrons, we have electrons. And some people can even break those down further. So they're not indivisible, but they are indestructible. Law of conservation of mass. Matter cannot be created or destroyed. So that point holds true. The next thing that Dalton said was that all atoms of a given element have the same mass and the same properties. The same mass, we know that this is not true. Why is that? Because of isotopes. Isotopes are versions of the same element that have varying numbers of neutrons. So for example, carbon-12 has 6 protons and 6 neutrons. Carbon-13 has 6 protons and 7 neutrons. They're both carbon because they both have 6 protons, but they have different masses because they have different numbers of neutrons. However, they both will act the same in chemical reactions. So the properties part, that holds up, but the mass part is wrong because we have isotopes. And then he said atoms combine in simple whole number ratios to form compounds. This is totally correct, and it's based on the law of definite proportions and the law of multiple proportions. And then atoms of one element cannot change into atoms of another element. This is not strictly true. There are reactions called nuclear chemistry, and in nuclear chemistry, you can take things out of the nucleus or put things into the nucleus, which means you mess with the protons and neutrons. And that means you can mess with what element you have, because the identity of an element is how many protons do you have. So this does not always apply. However, most reactions that you see are going to abide by this rule. Atoms are not going to change from one element to another. Once they start changing elements, you will know. You will definitely know, because you're going to talk about it a lot. So until you see that, this rule holds true for you. The next person to come along and revolutionize chemistry was named Mendeleev, and Mendeleev made the first periodic table. So the periodic table is a table that organizes elements into columns or groups based on their reactivity, how they act in chemical reactions. So this is a simplified version. The real one has 100 and some elements, but every column is called a group, every row is called a period, and back in Mendeleev's time, the periodic table was tiny and looked a little bit different, but now it looks the way that you would see it at ptable.com or on the wall of your classroom. And then back to the structure of the atom, there was this guy called Thomson, and Thomson did an experiment with a cathode ray tube. Okay, what the heck is a cathode ray tube? Well, hopefully this diagram will show you. So a cathode is a negative pole, an anode is a positive pole, and if you connect these to high voltage, you're going to start an electric current through this wire. And when that happens, the cathode is going to be negative, the anode is going to be positive, and this tube inside here was evacuated. There was nothing inside there. No atoms of any kind. So something from the cathode would start to travel toward the anode. So whatever substance the cathode was made out of, something came out of the atoms in the cathode and went to the atoms in the anode because it was attracted to positive charge, aka it had to be negative. And Thomson called these cathode rays. What they really were was electrons. So these cathode rays or electrons traveled to the anode, and nobody calls electrons cathode rays anymore, so you don't have to worry about that. And they would reach a magnet, And this magnet that Thomson had attached would bend these cathode rays, because if you have velocity, if you're moving, and if you have a charge, you will be affected by a magnet and your path will start getting turny. So these cathode rays would turn to different amounts, and how much they turned at what angle was based on their mass to charge ratio. So you don't get to know their mass or their charge, but you get to know what is their mass in relation to their charge. And what Thomson came up with was very different than what was known about the atom at the time, which led him to the revelation that the atom can be broken down into smaller stuff. So Dalton's model of the atom was, we just have a sphere. Thomson's model of the atom looked like this. So we had a sphere of positive charge and electrons would be dispersed throughout. And Thomson called this the plum pudding model. Plum pudding was a popular dessert at the time. My textbook says if you don't know plum pudding, think of a blueberry muffin. So like the blueberries are the electrons and the muffin is the positive charge. So there was no nucleus. It was just like a sphere and the electrons were distributed evenly throughout in Thomson's head. But this was not true. Next up we have Millikan. Millikan did the oil drop experiment. So in this experiment, he took a little spray bottle and he sprayed some oil into this contraption. And in this contraption, what we have going on is these droplets would fall through a positive plate and then they would get exposed to ionizing radiation. Ionizing radiation sounds really long and complicated, but really all that does is put a negative charge onto each of these droplets, because ionizing means giving something a charge and radiation is just, it's light, some form of light. So now we have these droplets that have a negative charge and they are being pulled down by gravity and they're being pulled up by an electrostatic repulsion from the negative plate. So gravity says come down to Earth, the negatively charged plate below them says get away from me. So eventually they come to an equilibrium where they're just floating there and they're not going up or down. And you can see this through the little peephole in the contraption. And Millikan used this to figure out, doing some math, the charge of an electron. And from the mass to charge ratio, he could also figure out the mass of an electron. So thanks to Millikan, we now knew the mass and charge of an electron. So moving on to Rutherford, what Rutherford found out was that the atom is mostly empty space. And he did this by taking radioactive lead, and radioactive lead makes little alpha particles, which are like one atom with some modifications, and these alpha particles went through a sheet of gold foil. And the gold foil is made of gold atoms, right? So what you would expect with the plum pudding model is that you would kind of get an even distribution of things just going through the foil, through the parts of the plum pudding that are less dense, right? The positive sphere of charge. And what actually happened is something different. Some of these alpha particles, which were positively charged, by the way, would hit this nucleus and bounce back. Others would just go through the negatively charged cloud of electrons. So what Rutherford found out from this distribution of some of them getting deflected and some of these alpha particle beams kind of going in the direction that he expected them to, is that the atom is mostly empty space with a little nucleus in the middle. So this was Rutherford's view of the atom. Again, not quite right yet. And then we arrive to Moseley. Moseley figured out that protons are more important than neutrons. So I don't know if he knew what neutrons were yet. I don't know the timeline of the discovery of the neutron, but basically what Moseley did was he figured out the atomic numbers of various elements, and he helped to order them in the table because now we knew the atomic numbers, and he figured out atomic number is more important than atomic mass. And then Chadwick discovered the neutron, and the books that I've read don't give an exact timeline on this, but I'm sure one is out there. So then we get to the point where it's like, okay, we know the nucleus, but what the heck is happening with these electrons? I told you that Rutherford's model wasn't right yet because we actually have an electron cloud. So what's going on? Well, this guy called Bohr tried to figure it out, and Niels Bohr, what he did was he took atomic emission spectra of various atoms, and emission spectra work like this. So you have an electron in an energy level, An energy level is just as you get farther out from the nucleus, electrons get higher energy. And of course, Bohr didn't know this yet before he did his experiments, but this is the way things are. And if you have light hit this electron, it gets excited and it goes to a higher energy. And if you let it go back down to the ground state, as we call it, it's going to release light. And the lights that it emits correspond to the energies of the difference between these two energy levels. So let's say that the energy difference between these two levels was 2. You could not have like a 2.1 energy light coming out of this atom because there was no energy level difference that corresponded with that. So all of these energies ended up making wavelengths that were discrete lines on the spectrum and not like a whole rainbow. Because when you're looking at colors and wavelengths, the wavelength of something is proportional or related to the energy. So if you can't have all different energies, you can't have all different wavelengths, you can't have all different colors, and these atoms are only going to emit certain colors. And Bohr discovered that every atom, like every different element, would have a different emission spectrum, and so it would have different energy levels going on. So the Bohr model of the atom was this. And then things started to get weird. So there was this guy called de Broglie, and de Broglie was looking at the properties of electrons, and he coined something called the wave-particle duality. And the wave-particle duality says sometimes electrons act like particles, sometimes electrons act like waves. How do you act like a wave? Well, light is a wave, right? Sound is a wave. You know noise-canceling headphones? How do noise-canceling headphones work? Well, they work that you have waves of sound going through to your ear, and the noise-canceling headphone is going to put another wave of sound, and they are going to do what's called destructive interference. Both of them are going to be there, and they'll be like, wham, goodbye to both of them. Not because they go nowhere, but because they cancel each other out. And this is, again, waves, not particles. These things don't have mass, so we're allowed to poof things out of existence if it doesn't have mass. So that's what a wave acts like, and electrons, as it turns out, can have that type of interference. Electrons can also act like a particle because they have mass. So that was de Broglie's thing, was that, okay, electrons do things the way that we know. They do sometimes act like particles, but they sometimes act like waves, which makes them basically like nothing else that we look at in the macroscopic world that we can see. So Heisenberg took that farther. He tried to find out where electrons were and how fast they were going, and he figured out that we can figure out the position of an electron. We can send something in to hit it, and then we know where it was. We can figure out the velocity of an electron. We can send something in to measure that. But the thing is, if we try to figure out the position and we hit the electron, we've just changed its velocity. We don't know the velocity anymore. If we try to figure out the velocity, we have to let it change positions, so then we don't know the position anymore. So we can't know both of them. The more certain we are about one, the less certain we are about the other. If I think I'm really sure where this electron was, I do not know how fast it was going. So that led to Schrödinger, and Schrödinger sat down and wrote some equations, and he figured out that, okay, we cannot know where an electron is at any given point, but we can know the probability of where it might be. So he started making these probability maps based on a bunch of math he did. And these probability maps are called orbitals. So you're going to learn all about orbitals in your chemistry class. And orbitals just tell you this is a map of how likely it is for the electron to be here. And when we say electrons occupy orbitals, that just means here's this electron. It follows this probability map in where it is likely to be. So generally, in an atom, they are probable to be just outside the nucleus, and as you get farther and farther away, they are less and less probable to be there. But more on that later. Oh, and Schrödinger also had this weird thought experiment where he was like, okay, all of this crazy stuff with electrons could never translate to the real world, because if we have an electron that's going between 2 points, and it's in both of these points at the same time, and we rig up a system so that when the electron is in this position, then it will break a bottle of cyanide and kill this cat inside this box. And if the electron is not in that position, it will not break the bottle of cyanide, it will not kill the cat. And Schrodinger's thought experiment was that, okay, this cat will be dead and alive in that box until we open up the box and we look at it. And then it will either be dead or alive, and it will not be both at the same time anymore. Too complicated. Way too complicated. Makes you very happy that we're only dealing with atoms and not with zombified cats. Anyway, that is an introduction to all the different people who contributed to our knowledge of the structure of the atom and what the atom looks like and how we quantify stuff in it. I hope this cleared some things up for you, and I'm looking forward to making more content for this chemistry playlist.